So this is an example for the first quadrant chopper. So we have a first quadrant DC chopper. The supply is a DC source of 220 volt. The load has E equals 0, L equals 7.5 millihenry, R equal to 5 ohms. The switching frequency is 1 kHz and the duty cycle is 50. So now we have frequency switching as 1 kHz. So T is 1 over F switching equal to 1 milliseconds. Tau is L divided by R equal to 7.5 divided by 5 milliseconds. Z equal to T over tau equal to 1 divided by 7.5 over 5 equal to 5 divided by 7.5, because both values are in milliseconds. So this is 0.6667. This is K. So to find, and the duty cycle K equal to 0.5 because it's a 50%. So 1, we need to find the average value of the voltage. So V out average equal to KVS equal to 0.5 multiplied by 220 equal 110 volt. Calculate the maximum and minimum values for instantaneous current. So we need to find I1 and I2. So I1 equation here, this is the equation for I1. So V source is 220, R of the load is 5 ohms, exponential K is 0.5, Z is 0.6667 minus 1 divided by E 0.6667 minus 1 minus E is 0 divided by R. And as you can see, if E is 0, for sure you will be continuous. The larger E you have, the more chance that you will have a discontinuous current. Okay, which means the higher speed of the motor, the higher chance that we will get into a discontinuous mode of operation. So I1 will equal to, let's bring the value here. So I1 equals to, okay, I will bring it from here. So I1 equal to 18.38 ampere. Then we can find I2. So I2, okay, just to save your time in the exam, it is this same equation, but the exponential is negative instead of positive. So just you will put negative here and negative here. So I2 equals to 25.659 ampere. So the current minimum is 18 and the current maximum is 25. So calculate the minimum and maximum current. Calculate the peak to peak current ripple, which we name it as delta I. The peak to peak current ripple or delta I is simply your max negative your minimum. Okay, so the current is charging from I minimum going to I maximum and going back to I minimum. So the current ripple or delta I is I max negative I min. So delta I equal to I2 negative I1. So we can find the current ripple to be 7.279 ampere. This is the peak to peak current ripple. Calculate the approximate value of the average load current. So the approximate value that I out average equal to I2 plus I1 divided by 2. Okay, so which equal to 22.02 ampere. I out average, this is the approximate. The exact will be V out average negative E over R equal 110. Negative E is 0 divided by 5 equal to 22 ampere, and you can see how close these values are. So today we studied the first quadrant chopper, or the first quadrant DC to DC converter, or the buck converter. Next lecture we will study the boost converter, then how we can add the buck and boost so we can have two quadrants, and then how we can do speed control using these, and this will be the last part of the course. Thanks. Okay, so today we will continue with our power electronics chapter. Last lecture we started the DC to DC converters as an application on transistors, and we studied the buck converter or the step down. Today we will start the step up or the boost converter. Then we will add the buck with the boost to form the two quadrants, and then we will see how we can have a 4-quadrant operation or H bridge. Before proceeding to the boost converter, we need to do some notes for buck converters. Last lecture we had this equation for I1 or the minimum current, and we mentioned that I1 has to be greater than or equal 0. So it is a continuous operation, and this is a continuity check, or we can write this as Vs multiplied by e power k z minus 1 divided by e power z minus 1 is greater than or equal E. If this condition is true, we have a continuous operation, and this is a continuity check. So as you can see, this is a condition for continuity, that this part is greater than this part. So you can see as E increase, as there is a chance of being discontinuous, as the EMF increase. And if we speak about motors, so as speed increase, there is a high chance that you can go into a discontinuous mode of operation. So if you are making sure or designing your circuit to be continuous, so you will design this at your rated speed, because at high speed there is high chance of being discontinuous. And also, as you can see here, we have K in this equation, and K is the duty cycle. So as K goes down, there is also a high chance of being discontinuous. So if you are designing a converter, you should design at K minimum. This is where you should design your system to be continuous, and you should design at E maximum to be continuous, and Z or Z is function of frequency, so it's T divided by tau, or it is T is 1 over F, and tau is L divided by R, so it's R divided by F L. So you can see that the frequency is an important factor. So as the frequency goes lower, as there is high chance of being discontinuous. Also, as the inductance goes down, there is a high chance to be discontinuous. So at any given K and E, you can find the inductance for continuous operation. So if you look at this equation, we have V source E power K, and Z is R divided by LF minus 1 divided by E power R divided by LF minus 1 is greater than or equal E. So as you can see here, you can find the inductance if you are given the frequency K, frequency E. So you can find the inductance, okay? So this is the variable in the equation. So what if E is changing and your duty cycle is changing? So you will find L at, as we mentioned, the K minimum, and you will find L at E maximum, and you will select, say this is L design 1 and this is L design 2, and you will select the maximum of L design 1 and L design 2, and then you have to insert this inductance in series with your converter. So this inductance will be inserted here. With this situation, you are making sure that at any given operation scenario, your operation is continuous. And this is how we design the converters, okay? And I think the problem set had some problems for designing the inductance to make sure that you have a continuous operation. So this is the last note for our buck converter, and the same note can be used for boost converter. So this is a generic way how you design the converter. So you insert an inductance here, and this inductance is inserted to ensure that we have continuous operation, or we have continuity. And this will be the design of the buck converter. Now we will start our second quadrant chopper or boost converters or step up. Okay, so I will sketch two sketches. One sketch is the one that follows the previous notation, and the second sketch is the most used sketch. So the previous notation, we had an R, L, and E load, and we had a source here. So we had V source, we had E, and we had R, L. What we did last time is we added switch here, and we added a diode here. For the second quadrant or the boost, we will reverse it. So we will add a switch here, and we will add a diode here. So this is a boost converter. So this circuit is a boost converter, or this is a boost. This is a boost circuit, and we can prove that this circuit will actually boost the voltage, as we will see. So the idea for boost converter, we have two modes: when the switch is on and when the switch is off. So when the switch is on, you will have a short circuit here, and when the switch is off, the diode will be conducting, and the switch is turned off, and you have this circuit. So here is RLE, RLE. Now let's see the simple concept that they built the boost on it. Now when you short here, when you have a short circuit here, the only source in this circuit is the EMF. And this EMF, this battery, if you have a motor, it represents the kinetic energy. This is represent the energy stored in the rotating part. So your motor or your machine is rotating. So this E is K phi omega. So if you have a speed, you have E. So if you have a motor and this motor is running and you shorted its terminals, so this E will, or this machine will be converted into generator and it will generate a current I. So this current I is going through the inductance, so the inductance will start to charge. So the voltage across the inductor will be in opposite direction to I. So the voltage across the inductor, V inductor, is L di by dt. So you can control how much voltage you have across the inductor by controlling di by dt. And you can controlling di by dt by controlling the switching. Now, once you open the circuit here, you are adding more resistance to the circuit. So for sure, without a question, this current will start to decay. So if the current is increasing in this situation, this is I versus time. In this situation here, the current versus time will start to decay. And it is decaying because you inserted an infinity resistance here. So the current will still going in the same direction. And why the current will still going in the same direction? Because of the inductance. So the inductance will not allow the current to reverse direction instantaneous. And as the current is decaying and the voltage of the inductance is L di by dt, so V inductance is L di by dt. So once the current starts to decay, di by dt will be negative, and the voltage across the inductor will reverse, which means that the voltage you can see here is E plus V inductor. So V inductor is supporting E to be larger than Vs, and now the current will go back to the source, or you are returning some of the kinetic energy from E to the source, and you can do regenerative braking. So boosting here means we are boosting E to be more than V. How you are boosting E to be more than V? You short-circuited the circuit, so you start to charge the inductance. Once you start to charge this inductance, this voltage will be added to E when you open the switch. So the voltage here will be E going up plus VL. So the voltage here will be E plus VL. And you are controlling, as we mentioned, VL by controlling switching, by controlling di by dt. So you are boosting this E. Okay, so you are boosting this E. Now, if we neglect the resistance of the motor, we say this R is almost zero. So the circuit will become as V source, diode, your switch, your inductor, your E. Or the common sketch is E, inductor, here is switch, diode, and here is your Vs. Just we flip this, so we flipped the circuit. So we started from E, then L, E, then L, then the switch, and then the diode going to Vs, diode going to Vs. So these two circuits are the same, but this is the most common circuit. So this is the second quadrant, or we call it boost. If we compare this to the first quadrant, so the first quadrant we have V source, we have switch, we had the diode, we had the inductor, and we had our E if we are neglecting R. So the interchange of the three elements, L, diode and switch can change between boost and buck. So the boost, you have the inductance, then the switch. For buck, you have the switch, then the diode and the inductance. Okay, so this one is a buck and this one is a boost. And in the boost, don't forget that we are boosting E. Okay, and this is related to what we started with. So note, if you have a battery and you need to boost this battery, what you will do, you will add an inductance, switch, and diode. So this is how you boost. If you need to reduce the battery, you need to reduce the battery voltage, you will add a switch, a diode, and an inductor. So this is buck. Okay, but for motors, we have V source, so we can buck or step down the source. So here is L, R, and E. So this is buck. And when we boost, we are not boosting the source, okay? When we boost the EMF from the battery. So we connect the boost like this. So this is the boost. So for motors, we boost E, or we buck, or we step down V source. But in application, when you have a battery and you need to boost it or you need to step it up or down, so this is how we do it. So differentiate between applications to batteries and application to motors. In motors, we are not stepping up or stepping down the source. We are stepping down the source or stepping up the EMF, so we are able to do regenerative braking. Now let's analyze the boost to convert. So as we mentioned, we will have our E. We will neglect, there is R, but we can neglect its effect, it's small. We have L, then we have our switch, we have our diode, and we have our V source. So if we go back, it is the same exact circuit we have here, okay? Now, if we look here at V out, so V out will be still positive or zero, but the current will be negative. This is I out. Why is the current negative? If this diode is on, you can have current going in this direction. If this switch is on, you have current going in this direction. So in both cases, the current is going back from the load to the source. So if we sketch the VI here, so our voltage is positive, but our current is negative. That's why we call this the second quadrant. And we called the buck as the first quadrant. So we call the boost as our second quadrant. Okay. Now if we look at the voltage here, V out, and this is your current I out. So if we sketch your V out versus time, when you close the switch, it is clear that V out is 0. And when you open the switch, so the diode will be on, so your V out will be V source. So your V out will be V source. And then it goes to 0 again, and so on. So this is V out, this is T on, this is your T, and so on. So if you find what is the V out average, so V out average is T minus T on. So it is this length multiplied by the height multiplied by Vs divided by the total time T, or it is 1 minus K multiplied by Vs. So V average for the second quadrant is 1 minus K V source. And if R is neglected, so V out average equal to E plus I out average R plus VL average. Okay, so this is KVL around this loop. The voltage of E plus the voltage of R plus the voltage of L is V out. So we said that VL average is always 0, R is neglected. So we can say that E almost equal to 1 minus K Vs. Please note, if R is given, you cannot neglect it, okay? Just we are neglecting it to illustrate the idea. In problem sets, you may be given R, so you just use it, you can use it. So E equal to 1 minus KVS, or Vs equal to E divided by 1 minus K. So the back EMF, or the voltage we have from the battery, is divided by 1 minus K. And you can imagine, if K is 0, you have E. If K equal 1, you can go to infinity. So if you look at this voltage, E over 1 minus K versus K, this is E divided by 1 minus K. So you will start from E and it will go to infinity. So you can boost the E up to infinity. So you can increase the back EMF coming from machine to infinity. So what is the meaning of this? So if you have a motor, and this motor is running, and this motor is supplied from V source, to be able to return energy to the source, you have to reverse the current. And to reverse the current, the back EMF E armature has to be more than Vs. And E armature is function of the speed. So based on the equations we have, we can get E armature divided by 1 minus K. This is the voltage that we can see. So by adding a switch here, a diode here, and the inductance of the machine, so it acts as a boost converter. So whatever E you have, you can adjust the K. So this term is more than Vs, or you are returning current to the source. And when you return the energy to the source, you are taking energy from the kinetic energy. So the kinetic energy, or the speed, will go down. So you will keep controlling K. So you will be playing with this K, so you can keep braking the machine using regenerative braking. So, and this is a very good technique to do braking, is the regenerative braking. So let's take a numerical example so we can understand the regenerative braking. So assume we have motor. This motor has a battery V source of 110, has a back EMF of 100 volt, and it has a resistance of 1 ohm, and the current going here is 10 amperes. And the effect of the inductance when we study steady state will have no effect, because the inductance will have no effect on steady state. So this 10 ampere is giving us certain torque. So this 10 ampere is giving us certain torque. And this 100 volt is proportional to certain speed. Now, if you decided you need to stop the motor, so stop the motor while producing same torque, or consuming same torque, which means we need to reverse the current to be 10 ampere in opposite direction. This is braking. And this means that you need to increase this voltage from 100 to 120. So we need the back EMF of the machine to be 120 volt. Why 120 volt? Because there is a 10 volt drop across the resistance, and it is this 10 volt will be added to 110, so this E should be 120. So this 120 volt equal to E divided by 1 minus K, and to do this, to be able to do this breaking, we need to add our boost converter. And this E is 100, so we can calculate what is the value of K. So we can calculate what is the value of K to stop this motor doing regenerative braking with constant current. But as we mentioned before, that the speed is different, the speed is changing. So how we can do this in real life? So if you have your motor, we can measure motor speed, and we can multiply this motor speed by K phi, which is the motor constant. So we can get E. Once we have this E, we will divide it by 1 over 120. This will give us 1 minus K. So this will give us 1 minus K. So to get K, we will take this value and subtract it from constant value of 1. This will give us K, and we will use this K to control the switch here. And this is a closed loop control to stop this machine using regenerative braking. But the minimum speed at which you can regenerate energy, minimum speed at which we can regenerate energy. So you need to be able at least to overcome the 10 voltage of the resistance. So the minimum we can reach is E equal to 10 volt. If E goes below 10 volt, we will not be able to do the regenerative. And you can find what is the minimum speed at which you will not be able to regenerate any energy from your machine. So all of this is just, we are illustrating the idea of boosting voltage and how the boost is a second quadrant.